Today we're going to spend a bit more time talking about the Michelson Morley experiment, and I'm going to explain in a little bit more detail what I was trying to say in my previous video. Okay, so the original purpose of the Michelson Morley experiment was to measure the motion of the Earth through space, which was believed to be a luminiferous ether. So there was an ether in the model back in the day, and it was thought that the Earth moved through this ether, through a static ether. And they were trying to use this experiment to see if they could measure the Earth's motion through this medium for the propagation of light. So the original purpose of the experiment wasn't to prove or disprove the existence of the ether. The purpose of the experiment was to see if they could measure the Earth's motion through this medium. So before I get into the thought experiment, I just want to read a section of this paper, Postulate of Light Invariance is Wrong in Principle, that was sent to me by one of my subscribers, Joe Dengelman. So the argument goes something like this. The classical principle of relativity, discovered by Galileo as early as the 16th century, claims that in all moving uniformly and rectilinearly frames of reference, so in all frames of reference which are moving uniformly and in a straight line, which Newton later called inertial, so these are referred to as inertial frames, all mechanical processes and phenomenon proceed in the same way. In other words, the laws of physics are the same everywhere, okay, including the speed of light. So the speed of light is included in the postulate, which I am referring to here as the laws of physics are the same everywhere, okay? So on the example of the ship moving at a constant speed, so Galileo imagined in his mind a ship moving at a constant speed. Galileo showed that no mechanical experiments carried out in the hold of the ship make it possible to determine in what direction and at what speed the ship is moving. For example, the objects released from the hands fall vertically relative to the moving ship, just as they would on the ground on planet Earth. Similarly, vertically with respect to the ship, objects fall as if they are released from the hands in a stationary ship or in any other ship moving at a different speed. At the same time, Galileo specifically emphasized that the principle of relativity is only valid for closed frames. Okay? Only experiments conducted inside the frame do not allow for determining the motion of the frame, but this movement can be determined if external signals, that is, the signals that go from other moving frames, are used in the experiments or observations. If you leave the hold of the deck, says Galileo, and look at the shore, you will see in what direction and at what speed your ship is moving. That is, Galileo strictly marked the most important feature of the principle of relativity. This principle is valid only within the inertial frame and therefore cannot be used in analyzing external signals coming from one moving frame to another. So what Einstein did is Einstein decided to generalize the principle of Galileo and to extend it to all electromagnetic and optical phenomenon. So let's try to imagine what, in fact, can mean such a generalization of the principle of relativity to all electromagnetic phenomenon. If we correctly understand the essence of this principle, the generalization of the principle of relativity can mean only that not only mechanical, but also optical and any electromagnetic experiments and phenomenon observed inside the inertial frame cannot determine whether this frame moves with respect to any other frame. The laws of physics should be the same everywhere, including electromagnetic phenomenon, okay? With this understanding of the extended principle of relativity, These phenomenon, just like the mechanical ones, will obey the principle of relativity and the laws of physics and will not allow us to determine the motion of the inertial frame. It is this extended principle of relativity that the Michelson Morley experiment confirms. So his interferometer does not allow us to determine the motion of the inertial frame, since the light source and the measuring device are inside this frame, that is, in an atmosphere moving with the Earth, and no external signals are used in the device. Similarly, the Michelson interferometer, if placed inside an interplanetary station like the space station, should be in full accordance with the principle of relativity and in no way react to the movement of the station and will not determine in what direction the speed of the station is moving. Okay, so basically what all that means is that the laws of physics are the same everywhere in a closed system moving at constant velocity, which Newton referred to as the inertial frame. So an inertial frame is a closed system moving at constant velocity. And by closed system, I mean a system that does not have access to any other inertial frame. Okay, so in the car example that I used in my previous video, okay, if the car were enclosed and it was moving at constant velocity down the street, then the laws of physics would work in your inertial frame. As long as you didn't look outside the window, you would not be able to tell what direction you were going. If you throw a ball up, it is going to fall and you're going to catch it in the same manner as if the car was not moving. Now, when you take the roof off and you're in a convertible, all bets are off because now you have access to another inertial frame, and that is the inertial frame of the air that is not blowing in reality. The air is at rest with respect to the Earth, and if you are moving with respect to the Earth, if you are in constant motion with respect to the Earth, then if you are in a convertible, you now have access to two inertial frames, and so now the laws of physics, as you observed them when you didn't open the roof, when you weren't in a convertible, when you're in an enclosed car, the laws of physics are maintained within that inertial frame. And once you take the roof off, then now you have access to two inertial frames, and now things don't work the same as when the roof was in place. So next what we're going to do is a little retroductive reasoning to try and determine whether the ether exists or not, okay? So we are not questioning relativity in this video, okay? What we're questioning is, did the Michelson-Morley experiment determine whether the ether exists or not? Because that is what people claim, even though that wasn't the original intent of the experiment. So what we're going to do is we're going to apply a thought experiment analogous to one that I heard Ken Wheeler use many years ago. And he asked a very simple question: how do you find a needle in the haystack? Okay, so the easiest way to find a needle in the haystack is to get rid of the hay. Okay, and the easiest way to get rid of the hay is to burn the hay. So if you want to find a needle in the haystack, probably the easiest and the fastest way would be to burn the hay. So basically you want to get rid of everything that is not the needle so that you can find the needle. So we're looking for the needle in the haystack here. We're looking for the ether, or at least evidence that the ether exists. And so what we're going to do is we're going to rule out all of the situations that we don't observe in order to ask the question or answer the question, can the ether exist? So we'll never be able to tell if the ether exists, I think, with any 100% certainty, but I think we can answer the question, can the ether exist? So did the Michelson-Morley experiment rule out the ether? Okay, and I think it didn't, but I'm not going to make any assumptions right now. We're going to start right from the beginning, and we're going to start with no ether, then we're going to add the ether, and then we're going to see, we're going to burn the hay, and we're going to rule out all the situations, and there's going to be one situation left that hopefully left that that is applicable to what we observe. So here is the simplified diagram of the Michelson Morley setup. What you have here is an emitter that emits a pulse of light, okay? Then we have a half mirror, okay? So the half mirror allows some of the light to go through, and then some of the light will get reflected, okay? And then we have a vertical mirror over here. We have a horizontal mirror up here, and we have a detector over here. So this is the standard setup of the experimental setup of the Michelson Morley experiment. So the first thought experiment we're going to do is with no ether and no motion. So the instrument is not in motion. There is no ether. Okay, there is no ether. And we're going to see what happens when the light gets emitted from the emitter in this situation. So this one's pretty trivial. Okay, there's no ether. There's no motion. So we know that the light is going to get emitted from the emitter. It's going to go through this mirror. Some of it's going to go this way, some of it's going to go this way. Now when it goes this way, it's going to reflect off this mirror, and it's going to go through, part of the signal is going to go through this mirror, and it's going to end up at the center of this detector. Now in the other direction, it's going to go through this mirror. Part of the signal is going to go through this mirror. It's going to reflect off the center of this mirror. It's going to reflect off the center of this mirror, and it's going to end up in the center of this mirror. So this is what the light paths would look like in this static situation. So again, the light goes along this path to the center of the mirror, goes up to this mirror, comes down and goes to this mirror. And the other path is it goes to this mirror, goes to this mirror, and over to this mirror. So this is a depiction of the light path, and this is what we observe. So at first glance, one might think that the Earth is not in motion because the instrument is in the inertial frame of the Earth. And so one might think that the Earth is not in motion and that there is no ether. But we know that that is not the case, because we know that the Earth is going around the sun, and we know that the solar system is in motion around the galaxy. There are all kinds of motions that we need to take into consideration. And so we can rule out the static Earth, the static instrument, and the no ether. Okay, so now we're going to add the ether to the situation. So here I added a background, which I can move around. So I can move the instrument. Okay, I can move the instrument relative to the ether, and I can move the ether relative to the instrument. Okay, so but first of all, we're going to do the yes ether and no, this is not in motion. So when the signal, so basically when the experiment proceeds, the signal leaves the emitter, it goes through the center of this mirror, it reflects back off this mirror and goes this way. Alternatively, it goes to the mirror, some of it gets reflected this way, and then ends up at the center of this mirror. So in this experiment with the ether, you get exactly the same behavior as you do with the no ether and no motion experiment. So here we have the light paths are the same for these two conditions. So, and this is what we observe. We observe the light going from here to the middle of this mirror to the middle of this mirror, etc. This is what we observe with the Michelson Morley experiment, okay? So we can't tell the difference in this experiment of whether there's an ether or whether there's no ether, okay? So we can't rule out ether, we can't rule in ether as well. But what we do know is that the instrument is in fact in motion. Okay, we do know that the instrument is moving because the instrument is attached to the Earth. It's in the reference frame of the Earth, and the Earth is in motion around the Sun. And so this is the situation that we need to accommodate for. So next we're going to do the situation where there is no ether, but the instrument is in motion. So the Earth is in motion around the Sun, and therefore the instrument is also in motion. Okay, so what's going to happen here is the emitter is going to emit a light pulse. Okay, and as this pulse is moving, the instrument is also in motion. Okay, so this is without relativity, this is without making any assumptions, this is playing dumb and saying, okay, what if we don't have an ether and the instrument is in motion? What happens to the light? Okay, so in this case, the light pulse is not attached to the instrument. Okay, light has no inertia, and it is physically not attached to the instrument. Now we have to assume that these mirrors, the emitter and the detector, are attached to a frame, which we refer to as the frame of reference. Okay, and so as the light is moving towards the first mirror, the instrument is moving from left to right. And so as you can see, the pulse of light is going to hit the mirror in a different location than it did before. Now I can actually stop there because this is not what we observe. Okay, this is not what we observe. What we observe is that the light hits the center of this mirror, and the center of this mirror, and the center of this mirror, and the center of the detector. Okay, so we can stop right there, but let's just follow this through. Okay, so now the light pulse is going to hit this part of the mirror. I'm exaggerating, and of course, it's about approximately a millimeter in the time it takes. If this was 10 meters from here, from the center of this mirror to here, to here, and to here, in the time it takes light to move 10 meters, the instrument has moved 1 millimeter if the Earth is with the speed of the Earth around the Sun. Okay, so we would be able to detect that. We should be able to detect that, but that is not what we detect. But if that is what was going on, then the light would hit this, the mirror here, okay, and it would reflect, it would hit, the first path would go this way, so it's going to hit this mirror in a different location, and then this is going to move further, and then it's going to hit the mirror in this location. So it's going to hit all the mirrors in the wrong location. Okay, similar with, so let's go back to the original, just go back to the original starting point. Okay, so now the light pulse leaves the emitter and it is no longer attached to the frame. And so then the frame is moving. Okay, and in this case, the light pulse is going to go through this mirror, but at a different location, and it's going to hit this mirror at a different location than it did in the original thought experiment with no motion. Okay, and this is not what we observe. This is not what we observe. But if this is how the universe worked, the path lengths, okay, the path lengths of these two light pulses is going to be exactly the same, and we're still not going to see a fringe shift over here. And this is what the computer program that I wrote accommodated for this situation here. Okay, and so I put the light pulse in here. Okay, so now I'm going to move the experiment. So that instead of the light pulse hitting the center of the mirror, it's going to hit the mirror here, and then it's going to hit this mirror here, and then it's going to hit this mirror here, and then it is going to hit this mirror here, but also it's going to take the path from here to here is going to be a bit shorter, and the path from here to here is going to be a bit longer. And the path from here to here is going to be a bit longer than it would have been if it hit the middle of the mirror. And so when I did my calculations, I discovered that these two path lengths are in fact the same. So if you're only looking at the fringes, first of all, these two light paths are not going to hit in the same location. So you can imagine that this light path is going to hit here, but this light path is going to hit here. So these aren't even going to intersect. So you're not going to see an interference pattern. And the time of flight, the length of the path that both light pulses, that both light trajectories take. So from here, it will be like this. So it's going to hit the mirror here, and then it's going to hit the mirror here, and then it's going to hit the mirror here, and then this one is going to actually hit the mirror a little bit higher. So they're not even going to hit on the same spot of the mirror, plus they're going to take a slightly longer path. Both path lengths are going to be the same according to my calculations, okay, but the path length is going to be just a little bit longer by a millimeter plus a tiny bit, and that's what my calculations show. And this is not what we observe. What we observe is more like that. Okay, so without an ether, and with the instrument in motion, and without taking relativity into consideration, this does not represent what we observe. Okay, so now what we're going to do is we're going to say, yes, we have an ether, and yes, I'm going to now clarify that the instrument is in motion, okay? So in this situation, we do have an ether, and the instrument is in motion. And what I realized with my thought experiment, that this turns out to be exactly the same as this situation. Okay, so what we have is the pulse is going to leave the emitter, and it's going to go in a straight line. It's not going to go in a curved path. Okay, it's going to, because it is no longer attached to the frame, because the frame is not attached to the ether. The frame is attached to the earth. Okay, so the instrument is going to move to the right. Okay, the pulse is going to hit the mirror at the different spot. Okay, and the instrument is going to move a little further, and then this is going to hit this mirror a bit sooner, and then it's going to go back, and then it's going to hit this a bit later because this will have moved yet again, and then it has to kind of catch up. So this is part of the problem of that they were trying to sort out with the Michelson Morley experiment, because this is not what happens in reality. Okay, so same with this mirror here. So the light was emitted here because the instrument was here when the light was emitted, and then once it is detached from the experiment, from the frame of reference of the instrument, it is now in the frame of reference of the ether. Okay, it is no longer attached to the instrument, so it's just going to take a straight path, and it's going to hit the mirrors in different spots. And if the instrument is moving really quickly, it might even miss the mirror. Okay, so this is a bit of a paradox. This is totally what we don't see. We do not see the light pulse missing the mirror. We do not see the light pulse hitting the mirror and the detector in different locations. Okay, so this is definitely not what is happening. We do not have a static ether, separate from the moving instrument. Okay, so this cannot work. This will not, even though the light paths again in this experiment, the light this is the same calculation I did with this one without the ether. Without the ether and the ether, they're exactly the same, because once the light pulse leaves the emitter, it is no longer, it's still taking a straight path. It is no longer, in the frame of reference of the instrument. And so this is what would happen if this was true, but this is not true, because what we observe is in fact this case right here. Okay, what we observe is the instrument. We observe the light leaving the emitter, going through the center of this mirror, hits the center of this mirror and the center of the detector. This is what we observe in reality. And I also want to point out that this was a static ether, that the ether was not in motion, that the instrument was in motion relative to a static ether, which was the original assumption of the Michelson Morley experiment. Okay, so remember, the Michelson Morley experiment was developed before we had relativity. Okay, relativity was an output of the Michelson Morley experiment, and so not including relativity into this, what I'm trying to do is I'm trying to rule out different situations. So we can rule out that, yes, we have an ether, but the ether is static, and yes, the instrument is in motion. Okay, so we can rule out static ether without relativity, with the instrument being in motion. Okay, so next we're going to do the situation where we do have an ether, but the instrument is not moving and the ether is in motion relative to the instrument. And this is what they refer to as the ether wind. And so here what we're going to do is we're going to have the ether in motion, okay, relative to the static experiment. So in this case, we have the light pulse, which is emitted from the emitter, and as soon as it is emitted from the emitter, it is no longer in the rest frame of the instrument. Okay, it is no longer in the rest frame of the instrument. Instead, it is in the rest frame of the medium for the propagation of light, the ether. Okay, so what's going to happen is it's going to take a path. Okay, it's going to take a path like this. Okay, only as it's doing that, it's going to take a straight line path, not a curved path, not a diagonal path, but a straight line path. And at the same time, the ether is moving. So the ether is going to be moving. The light pulse is at rest with respect to the ether now. It is not attached to the frame. Once it's emitted and it's propagating in the medium for the propagation of light, it is now attached to the rest frame of the medium. And I think this is where I had trouble. This is where I feel like maybe they made a mistake in their thought experiment, assuming that the ether wind would create a diagonal path. So in the video that I showed you last time, what they're doing is they're depicting the ether flowing from right to left. Okay, and then they're depicting the light pulse as if it's going on a diagonal. Now, if the pulse was started out in the ether, if it started out straight, it's going to continue to go straight, okay, in the reference frame of the ether. Okay, so they're showing it taking a diagonal path in this animation, okay, and then they show it to continue to take another diagonal path on its way back down. But that is not what I'm seeing in my thought experiment. Okay, in my thought experiment, what I'm seeing is that the pulse, once it gets released from the emitter, it is no longer attached to the frame of the instrument because it is propagating in the medium for the propagation of light. It is propagating in the ether, and so it is at like it is in the rest frame of the ether. Now, of course, in this thought experiment, the ether is in motion. So basically what's happening here is the light is going to take a straight path to the mirror. The bulk of the ether is going to be moving. Okay, the bulk of the ether is in motion. Okay, so the ether is in motion, and the path that the light takes is going to be at rest with respect to the ether. And so in this case, it is going to hit this mirror in a different location. It is going to hit here, and then it's going to hit this mirror in a different location, and then it's going to hit this mirror in a different location. And this is going to be identical to what happened before. So the static ether moving instrument in my thought experiment, okay, is going to look the same. It's going to be the same and measure the same as the static instrument with a moving ether. Okay, so these two are going to look very similar. They're going to be exactly the same in terms of quantification. There is no difference between whether the instrument is static and the ether is moving, or if the ether is static and the instrument is moving. And that is not the problem of relativity, okay? Because the real problem here is in a static ether and moving instrument, or in a moving ether and static instrument, the light pulse is not hitting the mirrors in the correct location. The correct location is when the light pulse hits the center of the half mirror and the center of the horizontal and vertical mirrors and the center of the detector. Okay, so the only time this can happen if there is an ether is if the instrument is at rest with respect to the ether. Okay, so if the ether is moving, the instrument must be moving, and if the instrument is moving, the ether must be moving. And that can happen actually two ways. So historically, they talked about ether drag, where they talked about the Earth dragging the ether, and I'm not sure that one is correct. Truthfully, it makes more sense to me that the ether is in motion and the instrument is in motion. So if the ether is in motion, then the Earth is in motion. In other words, the Earth isn't dragging the ether is moving. Sorry, the Earth is moving with the ether. The ether is moving the Earth. So the Earth isn't dragging the ether is moving the Earth. Okay, and this leads to, instead of a static ether, it leads to the idea of a dynamic ether. Now, if there was no ether, okay, then how can we explain that the light, because the instrument is in motion, how can we explain that the light pulse hits the centers of all the mirrors? That's very difficult to explain without a medium for the propagation of light, because I can't think of any reason why once this light pulse exits the detector, because light has no inertia. Now, if this was a bowling ball, then yes, I would expect it to have the inertia to follow the path of the instrument and behave as if I were in a car throwing a ball up and catching the car. but light has no inertia. Yes, it has energy. Yes, it has momentum, but it does not have mass. Light doesn't have mass. I've been told that a million times. I believe that it's true. And mass and inertia go hand in hand. Only objects with mass have inertia. So I can't think of any reason why once this light is emitted, if such a thing can happen without a medium for the propagation of light, I can't think of any reason why it would follow the instrument. Okay, so the only thing that makes sense to me without relativity is that the Earth is at rest with respect to the medium. The instrument is at rest with respect to the medium. And how that happens needs to be, well thought out, of course. Is that a possibility? I don't think the possibility of the dynamic ether, have the Earth following a dynamic ether. So the Earth is at rest with respect to the ether, but that doesn't mean that the ether isn't in motion. So in terms of ruling things out, in terms of the retroductive burning of the hay, okay, I think that we're able to rule out the no ether and no motion because we know we're in motion. Okay, and I think we're able to rule out that there is an ether, but we're not in motion because we are in motion. And we're able to rule out a static ether with a moving instrument, and we're able to rule out the static instrument and the ruling ether because the light does not hit the center of the mirrors in all of these circumstances. So the only one, so prior to relativity, without relativity, the only one of these thought experiments that can't be ruled out is that the instrument is at rest with respect to the ether. Okay, so I know they did talk about the possibility of ether drag, that the Earth is dragging the ether, but I don't think they were thinking about that correctly. And there's also the possibility that the ether is moving the Earth. And so it's kind of like the lazy river where you throw a stick into the river and now then the river is flowing with, the stick is flowing with the river. The stick is at rest with respect to the river, even though the river is in motion. And so I think there's a possibility that all of the motions that we see in the universe are actually ether in motion, and that matter is just following the ether. And this would explain, so every location in space and time would be at rest with respect to the ether, but when you look at different reference points in the universe, you're going to see different inertial frames. And so I think that's another possibility that we maybe haven't thought about. And of course, relativity can also save the whole situation, but it's possible that relativity is just a mathematical formalism to help us work out the math, and may not be necessarily a physical phenomenon. And so that needs to be looked at further. But in terms of the postulate that the laws of physics are the same everywhere, in that the sensations that we feel in a moving car going at constant velocity feel the same as the sensations in a car that's not moving, as long as there's a roof on the car. That postulate this kind of fits in with that postulate, because in the moving car, the person sitting inside the car is at rest with respect to the moving vehicle, and of course the air in the car is at rest with the moving vehicle, and that is why when you talk to each other it sounds the same as if you weren't moving at constant velocity, or if you were just standing outside in a non-windy day. So hopefully this is a slightly better video than the last one I made. I wanted to clear up a few things regarding this angular path that this misconception that there would be an angular path if there was an ether wind. I don't think, and maybe this, I've seen a lot of videos that kind of explain it this way, and I don't think this is correct thinking. And so there are other ways of solving this problem, but I don't think the ether wind is going to make the light go in an angular path. And so that was sort of the point I was trying to make in my last thought experiment. And so I'm going to leave it at that, and because this video is getting kind of long, and so hopefully you appreciate what I'm trying to say here. And I am not going against relativity here. Relativity saves the whole day. It works out, everything works out, but whether it's actual physical phenomenon or just a mathematical framework to help us sort out the relationships between different inertial frames, I think that's where relativity is really helpful. But in terms of understanding why does it feel like we're not moving when in fact we're moving at almost 30,000 kilometers a second around the sun, and we don't feel any forces at all. So I think this kind of explains this phenomenon very nicely.